videos on here, so I don't feel like I'm talking to myself during the presentation. This is a bit of a downside of doing, online workshop, but at the same time, I'm very glad to see so many people from different areas connecting at the same time. Um, so when I was thinking about what to write in this presentation, I was thinking about big data, geomorphology. As Stuart said, I'm a geomorphometry, so I'm used to work with data. And I feel like now everyone is talking about big data. But all in all, after I prepared this presentation, after thinking about it, I got to somehow the conclusion that I'm not sure I know what big data are in reality. So, um, my big question for big data was actually, are we really looking into everything we can look into, or are we looking just through a lens that it's given by different background that we have, different tools that we have, or different data sources? So I tried to build this presentation around these questions. Of course, we can agree, we can disagree, but I hope this presentation can at least spark the discussion on big data in geomorphology. Um, like I said, I'm a geomorphometrist. I've always worked with data more than field surveys, for example, and it's always a struggle to get meaningful information from the data we have. And I think the quote that I'm showing kind of summarize my experience in geomorphometry. If we do torture the data long enough, if we do work on the data long enough, we are able to get meaningful science from it, but it's a long process. So the first thing I tried to do was try to see in literature, the modern literature, what big data are. So I simply put keyword search without actually adding a field. And to my surprise, I think we are at the stage where big data is used by everyone from medical science, technology, data analyst, environmental science, but it's a big bunch of words that actually are not really connected one to the other. And the thing that was coming up to my mind, there was always something about big advantage, big challenges, big struggle, and many things were coming up as a cluster of data, like data problem or ethic on data, which is also something that we don't consider, for example, many times. Uh, the big data challenge or the big data framework of using. And I feel like this is the reality in all the disciplines that are using big data. Some of the disciplines like geomorphology are still very much, which is a good thing, uh, with boots on the ground. So big data is new, but it's still in the early stages. So when I went to actually trying to find big data in geomorphology, so I added one simple keyword to my search, what came out was a lot of things connected to big data, from landslide analysis, from data analysis itself. But there's really not groups of work using big data. I feel like many people use the word big data, and we still cannot define what big data are. But anyway, it's something that is coming up in the last 5 to 6 years now, with the access of open data, with the access of tools like Google Earth Engine, for example. There's a lot of work done there saying they're using big data. And if I have to think, what they can offer us, I do know and I do feel like big data are giving us, that are putting geomorphology into a data-rich science. We are going further out of the limits that we had before from field surveys, for example. We can access location that I don't think we would ever been able to reach before, for lack of sources, for lack of even funds, or for lack of tools to get there. But I don't think this is something new. In the field of at least computational geomorphology and even, technical geomorphologies, we always had some big leap and big jumps in publications, analysis, because of new technologies. Myself, I grew up and I was born with LiDAR. So when I started working in geomorphology, LiDAR was a very big advance in hill slope modeling or terrain modeling. And there were questions on where is this technology putting us as geomorphologists? Is it transforming geomorphologists? There was a very good paper by Heather Biles about where is the technology putting us as geomorphologists. There were paper by Roaring and others. You are here, and I think it's a very good question because when you get a new technology, you know what you're doing, you know what you would like to do, but sometimes it's still brand new and very hard to tackle. But of course, all this new technology gave us boosts in research. Sorry. But at this point, when I think about big data, sometimes I wonder if we have maybe too much information that we can tackle. And I was reading about other reviews. And the question was, are we drinking from a fire hose? How much of this information that we can get from big data is it actually meaningful for us from an environmental and geomorphological perspective? Um, Many of the work referring to big data defines big data based on 4, 3, 5, 6 V's. Let's say the most common way of speaking about big data is the 4 V's, which express the volume of the data. Of course, we have so much information coming from many, many different sources, and this brings the second V, which is the variety of data. Um, One major characteristic of big data is the velocity at which we produce information or at which we can gather the information. We have real-time sensors. We have the advantage of even citizen science, allowing random people everywhere to add their information somewhere about something. But all of this, the volume, the variety, and the velocity also brings up the question of veracity of the data. How good are these data for us, and how uncertain they can be? And I think some of these points will also be covered in the following talks about reproducibility or about data sharing. So I don't want to go too much into details, but at the same time, I think everything is connected. Um, Many of the things that I'm going to showcase after here and that I use to build up my presentation are taken from some works which I found very interesting. They were talking about big data in geography, um, with raising interesting question, and I think it feels like this is also appropriate for geomorphology. Um, So my big question at the beginning was, we have big data, new data, or are we looking into old problems? Like I said, I work mostly with geomorphometry, and we trying to figure out how to use data on a computer. In 1987, I don't know if people are familiar with it, MicroDem was created, was one of the first software allowing to do terrain analysis from high resolution at that time, terrain data. And I thought it was very interesting to read the description of the software, which in 1987 was able to manipulate large elevation data set with 90,000 points per set. And here I'm reproducing a very nice reconstruction of a hill slope from LiDAR. And we have a very small hill slope which has 35 million points with 15 centimeter distance one to the next. And actually, this landscape is by Williams et al. Is surveyed periodically. So we don't have just 3D data, we have 4D data. And this is not big data, it's just a hill slope. But compared, to the evolution of the topography and, the topographic survey, this is a huge data set might not be a big data yet. Going back to the software MicroDEM, it runs on industry standard MS-DOS computers. I had to Google what that was because I'm not old enough to have had one of those. When I moved to Connecticut in my research, I found out that we had an HPC computer, and I thought I did all my PhD with a 1 GB RAM desktop that I had to figure out how to get to work with LiDAR. If we think about big data, we're not just talking about the amount of data, we're also talking about the support that we need to handle that information. And this is what struck me the most. Back then, 1987, MicroDEM was written in Turbo Pascal, but allows easy modification and customization of the software. And if I have to think about programming codes, which it's not purely geomorphology thing, but with the advantage of technology, with data sharing, with big data, we are creating new skills for ourselves as geomorphologists. It's not just about going to the field, which is the starting point. We require programming skills, we require computer skills, and that sometimes can create a sort of detachment from reality. And also, it was very interesting to see that in 1987, the software was created so that everybody should have been able to modify it very easily. But anyway, if you were not able, or very capable on the computer, the executable should have been able to run without any modification and without requiring any knowledge from your side. I don't think this is the reality anymore. It's been, 40 years. We have more data, we have more softwares, we have more hardware, and we are back to before 1987, where maybe we cannot really use all we have. So, my major points that I wanted to discuss over big data, new data, or old problems is about the statistics that we can get from big data. Yes, we have large coverage. Yes, we have plenty of sources, but is it really a population of data that we're looking into? So, like in this case, 99% of people were lonely and wanted someone to talk to. Yeah, okay, those were the only one that actually answered the phone. So we do have big data, but are we looking into samples or population of data for the analysis that we want to do? The next thing I wanted to highlight with big data is the issues of the mathematics that we can do on them. With the large amount of data, can we really infer a meaningful geomorphological information from them? Or are we just looking into correlations, which is not always why something is happening? Like in this case, everybody that went to the moon was eating chicken, so it's the chicken that brings people to the moon. I feel like maybe with big data, we should also look into this issue. And finally, big data, it's still about technology, production, and use of data. And with any type of evolution of technology, we do have a lag phase between when the technology starts, when it starts to be used by, in our case, geomorphologists, when it actually becomes so meaningful that we can create science from it. But it also gets to the point where it somehow stays stationary in terms of new science, in terms of new data, and in terms of production, if we want about published papers, for example. Um, so let's go to the first point about statistics. Is it a sample or a population that we're looking into? As researchers, as scientists, geomorphologists, we want to have a representative sample to draw our conclusions. And our sample was given by the fact that we couldn't access everything. Physically, by going on the field, you can only you're physically limited to the extent that you can reach, the number of samples that you can get, the number of study areas that you can have. And as we are human beings, other than scientists, we have a mindset on how we go to the field and we collect data. We have preconceptions. So we have an idea, we have a theory that we want to address by sampling the population that we cannot access. And these ideas and theories that we want to address, of course, limits the amount of data that we are going to collect because we want to get the response that we care about. We have foresight. We have a goal of our study. And this is also shaped by our knowledge. So even in this case, the sampling of the population is biased, not in a negative way, but unbalanced towards the goal of our observation. And of course, we have forehaving. Each one of us has a different training, has a different background, has a different knowledge about tools and instruments used. So our skills and even the institutions we come from somehow limit, in a way, what we are trying to achieve. And all of this is sedimented into us because we're human beings. That's how we work. And why I go through these points, because I think this reality, it's also true for data, which are not people, but the way data are collected, and data are collected by people. So if I have to keep this way of thinking and I have to move to big data themselves, nowadays we have much more ease, potentially, to collect the data, store them, and process them. And this means that potentially we're not looking into samples anymore, but we're looking into entire population because of the volume of the big data, because of the velocity at which they are captured and produced, and because of the variety of the sources. So potentially, statistically, you might have numbers large enough to define that you're looking into populations. But is it really a population? That would be my first question. So we said that as researcher, we have preconception on how we go on the field. Let's keep one big data. I'm a geomorphometry, so I look into terrain data. We have global terrain data nowadays. Is a global dam a real random sample of the terrain? This is just one example. This is the ESA 10-meter terrain data, which technically is global, but it's founded by ESA, so it only covers Europe at 10 meter. So, and all islands of those countries that are within Europe. Of course, we have a global terrain data at 90 meter or 30 meter, but the 10 meter one, it's not really a sample. It's a specific choice of creating the terrain for those specific countries. And I'm not saying this, in a political way, just to showcase that big data is not necessarily sampled randomly. With big data, many people talk about citizen science data, not because of the variety, but because of the amount of information, the speed at which it can be captured. And this is an example of the British Geomorphological Society iGeology app that allows people to interact and has a crowdsourcing element, for example. If we want to use crowdsourced data, is it really a representative sample to be used? Or is it because someone at some point was interested in that project, so it was already starting with a biased idea on your project? Or maybe someone in that moment in time accidentally had access to the technology to give you the crowdsourced information. So it is random, but it's not that random to be a whole population of data. still a random selection of an error amount of information, despite the fact that it's a very large information. Foresight. Big data are not systematically surveyed. And they are, of course, a patchwork of multi-scale, multi-time, multi-resolution data. Here on the left bottom corner, I showcase the global heat flow database. It's about 70,000 points. This researcher binned them by latitude and longitude. And what you can see is that of this big data, they are not really random because we have peaks of areas that are sampled more because of more researchers working in those areas, because of more funds invested in those areas. So again, still a very large, but not a sample, but not a population from which to infer statistics. That doesn't mean that we cannot use them, but I think it means that we should always keep into mind that big data, the large volume of data does not make them a sample significant enough sometimes. We need to acknowledge their limitation and their limit in general in capturing what we want to show. I'll move again. For having, as researcher, we do have an idea of what we want to show, and we have skills and knowledge that comes from our training. When you talk about big data, these skills and knowledge are very, very different depending on who creates the data. It could be someone that has zero skills in the science factor, the geomorphological field, but it might be very, very high skilled in the data science. The forehaving are also different depending on who uses the data. You might have, I've had very nice conversations, for example, with data scientists, purely data scientists. They would know exactly how to organize those data from their perspective, but they were struggling to try and give them in a meaningful way to me so that I could do some geomorphology from them. And of course, this can cause issues on communication, translating data between who creates them, who uses them, and who makes them available. And again, I'm saying this because I think it's something that we always have to keep in mind. Moving to the next old problem or new problem, like I showed earlier, big data are seldomly random, samples very big population. If we want to make science out of it, we need to consider the fact that we can for sure see correlations, but that doesn't mean that we can infer a why from them. Just for fun, if you didn't know, there's 66% chances that if there's Nicolas Cage in a movie, there's going to be someone drowning in a swimming pool. So it's a very high correlation. Of course, that doesn't mean that it's a cause and effect information. In terms of causality in geomorphology, this is a very long science. And we want to look for causes. We are not just looking into correlation. We want to get meaningful information from our data. And that's why, again, I'm talking about new data, but old and known problems. A few years ago, I also attended a very brilliant lecture from Coulthard at EGU on geomorphic apophenia. Are we inferring meaning where there could be none? I think having the vast amount of data that we can get today still to bring us back to the importance of finding a why and not just it happens this way. And going back to an example for here, this work, they used crowdsourced data to try and infer a landslide susceptibility with machine learning. And they created different attempts and different models. And what struck me was that most of the models were actually very good correlated with the reality, but none of them was giving a plausible, geomorphologically plausible prediction of the landslide, because the landslide data set was surveyed by people in the area that was more easily reached by people. For example, they were surveyed because they were high impact landslide. So it wasn't a very large sample. It was a specific sample of only impactful landslide. And again, the most important point was that we were not able to, they were not able to create a geomorphologically plausible prediction. It was a good prediction by numbers, but sometimes it was not meaningful from the process perspective. Um, so we said about the big data have volume, they have variety, and they are very fast. I am going back to the description of the micro DEM program. You know, it was able to be run on industry standards computer. The evolution of big data and the amount of data that we get follows the evolution of technology. And what is important to think is the speed at which technology is growing in terms of even instruments that we have for field surveys, not just computers to elaborate the data. It's not a constant speed. We have very big accelerations in, for example, remote sensing techniques. At the same time, the computer might not be as fast, so the normal scientists with lower resources might not be able to actually tackle that information. At the same time, this evolution of technology brings to the table the fact that we need different skills. And not all of us have the background to do them, have the resources to grow those skills, or sometimes we prefer not to. We might have to rely on someone that has a huge background on IT to work on an HPC computer. And I'm going back to, for example, a personal example. When I started working with an HPC, I can write my code to do my analysis from the geomorphometric perspective. I am not sure how to tackle the runs on an HPC because I don't have the skills to work on a Linux computer, which is my fault. I never had to use one, so I'm not sure. So I have to rely on someone that knows that, but at the same time, they don't know what's the point of my study. So we have to grow different skills and we have to grow also different ways of communicate our science. We have to keep grounded to the discipline because of course that's what we do, but we need to make our ideas and our knowledge translatable into a domain which is mostly not ours, which is, for example, the technological domain. In terms of data velocity, it's not just the speed at which technology evolves, but it's also the speed at which we can get information. We are nowadays able to get geomorphological information almost at real time for processes that sometimes are not really real time and they are processes that might take centuries to grow. At the same time, the theories and the meanings that we are trying to address or explain might describe information which is much slower than the speed of the data we're using. And sometimes I feel like there might be a very big gap between the speed at which the technology provides us the information and the speed at which we can actually use that information. Is velocity and speed always that important when we talk about process that takes centuries, millennia, geological eras to run? Is the speed always meaningful for us? And I tried to search in terms also of theory of geomorphologies, where we are, how we got there, and where is this technology bringing us to. So there was a very big jump in geomorphology science from the 60s to 2000, 2010. Quantitative geomorphology was actually consolidated, and even computational geomorphologies become a day-to-day use, let's say, for many researchers. There were very big research and very big sparks into the discussion of geomorphology itself and geomorphological processes. Thanks to the amount of data we had, thanks to the new technologies we had to survey, and thanks to the new technologies we had to elaborate the data. And we did have tools to either confirm or deny old paradigms in geomorphology. Most of my research at the beginning was, for example, on river network extraction, which dates back to when the first terrain models were created. When LiDAR came out, many researchers like me were trying to find different ways of capturing drainage network, for example. And this was sparked by the fact that we had high resolution terrain, we had continuous data set, and we had to find different ways of extracting the network. But then I tried to look into the science in the 2000, 2010 timeframe, and what I saw was there was a big jump in the way we had of handling the data rather than the data themselves. If we think, and again, I'm going back to my experience, from point data, we started working, for example, with digital terrain models, so a 2.5 view of the landscape. Now, scientists were starting to go back to using point clouds because the amount of technology we had to elaborate point clouds was much higher. So we could develop new methods of working with geomorphological data in 3D with point clouds. However, this brought also the fact that we needed more multidisciplinary and interdisciplinary background, not just the science part, but we needed the coding aspect. We needed the computer science aspect, but we also needed the database, let's say, skills to organize this data so that we could actually reuse them or pass them to someone else. But at the same time, there was really no new spark or new things. Not in terms of, striking new research, but rather very interesting piece of works on new ways of seeing things. Um, and in terms of velocity of the data, having high speed information, meaning that we can collect them very quickly multiple times, having very complex data gives us also a meaningful information in terms of geomorphology, depending on what we want to do about it. I modified this image from actually a business presentation where they were talking about complexity of business data and the business value on selling the data. But I think mostly it's the same for every discipline. So we hope to get very important, meaningful information from data if we are able to forecast and simulate what will happen in the future, also for geomorphology. But for geomorphology, for us, it's also very important to analyze why something happened and understand the process behind it. But that doesn't give it, like in this presentation alone, geomorphological value, it's still a very important one. So if I have to consider big data, how much of the information that we have is useful for us to identify a model, a process? Mostly, when we look into geomorphic processes, many of them are actually outliers. They're not the norm. However, if we have so many information and so many big data, how many of these outliers become the norm just because they are oversampled rather than meaningfully sampled from the data? Most important thing in my mind is that geomorphology is nonlinear. And I took this very nice graph from an unpublished presentation of Phillips, and it struck me because geomorphology and geomorphological process do not always have a very sharp definition. Many times they are a transition between different stages. They are a transition in amount, in volume, and in time. Many of them are chaotic, and sometimes we're not sure we're actually capturing them, even if we have terabyte and petabytes of information. Now, with big data and machine learning, for example, it's very nice to produce random behavior, learn from the patterns, but again, can we do it meaningfully? And what we still have to keep in mind is that we are always looked into a very fine, discrete sampling. So even when we have real-time information, as much short as the time of sampling is, it's still a discrete sampling. And the limits and the boundaries of geomorphologies or geomorphology are not always that discrete or sharp. Um, and that brought me to think and read also about many other works that were discussing on, is this fast change life of data? Is this quick sampling? Is this the amount of information we have useful for us as a geomorphologist? And I read this very nice publication by Stuart Lane talking about slow science. And I think it actually hit me. Many of the sentence, many of the things he was saying is that at, we are at the point that we might have more data than ideas with which to interpret them. And this is not always our fault, but it's the reality of the fact many times. At the same time, Lane was saying that we do have much more to read because of the amount of information, but sometimes the quality of what we read is less clear. And there are not striking works coming up. There are not that many paper that makes you feel, wow, I've never thought of that. And if we have to think about how technology boosts our science, and this is about big data in general, but it works, I think, even in our field. You know, we have the technology trigger. Everybody heard about the new technology, everybody starts using it, and we all have very big expectation about what we can get from this data. And then, you know, we go down in the through the disillusionment of the data that we cannot use them all. We figure out that we can find something useful for us, but then we still are limited in what we can make out of it. And one of my fear, and it's not just mine, I think, is that sometimes with the amount of information that big data give us, we might need someone that is more of a data scientist, and we are more analyzing the datascapes than actual landscapes. And probably we could risk the fact that the environmental expert comes back into a second place compared to the data scientist that has to organize the data. However, a pure data scientist cannot really organize them in a meaningful way for example, a geomorphologist to use them. So it is very important to always remember that everything we do in the datascapes has to be brought back to the physical landscape. And we need to consider that this one-to-one translation sometimes might not be possible. Um, so at the end, from the point of view of having big data, petabyte, gigabyte of information, what we actually want is a very small uh, handle knowledge that we can gather from the data. And it should be a meaningful and refined information. The quantity of the data, it's not directly related to the quality of our models. We could have models to where it doesn't matter how much data we feed them, if they're not created correctly, they're still going to be um, not good models. We could have models that the more data we feed them, the better they work, and this is the straight line. But if we think, for example, about machine learning, the quantity of the data, it's not what makes our model works best, but it's the quality of information that the model trains upon. And if we start training the model with wrong data set, it's going to produce very, correlated results, but they're always going to be very wrong. We could also have models that works very well, even if we have few points of data or we have millions of points of data. And what we hope to get is the fact that from the very big amount of information we get meaningful science. Um, and this brings back the point of veracity and variety of the data. And here I was reading on Science a few years ago the parable of the Google flu, which sounded very neat as a striking point. It was Google predicting influenza, so nothing geomorphological, but the point that Google was predicting it wrong, even if it was trained on the right data. And if I go back to the geomorphology itself, again, when we talk about big data, I'm sorry, and also many other disciplines, when we talk about big data, you should make a very big distinction between quality and quantity. And this quality of data depends on many informations. Like I said at the beginning, it depends on how we look at the data or how the data handler is trained, the experience they have, the background they have, how whoever samples the data was trained and the background. It also depends on the tools we use to work on the data. Each single algorithm has its uncertainty, each method has its limit of applicability, and it might be working perfectly for one data set, but work very bad for others. Most of all, we are talking about a science that is extremely heterogeneous in space and times, and the heterogeneity sometimes happens across space and time scales. And if we think about the current times where there's strong modifications of the landscape by humans, this heterogeneity of process might be unconnected physically, but it might be there might be causes and relationship across continents, for example, because of political actions. We are used to have many sources of data. This is not new. And like at the very first slide, I was saying it might be evolutionary rather than revolutionary. We have many techniques to sample different things. And this was known to us working in computational geomorphology. With the big data, we have even more and in even less organized way. And here, this is an example of landslide sampling, where the same number of samples was collected across different sites. And the horizontal line is the average value of the slope angle. And then the boxes are the presence or absence of landslide. Depending on where the location was sampled from, we had a very different range of values compared to the average of the whole data set. And it was always the same number of samples. I also saw some works speaking about how we should share data to others for others to use. And I think this is going to be also a topic for the next talks. I feel like in many other disciplines, there has been efforts done to create standards. Sometimes because we're very much with boots on the ground, we have very hard time to share things in a meaningful way for others. And big data are fed into the system continuously without a real organization behind, without a real thought process, or with billions of thought process behind every single data set added to the system. One thing to consider is that we should go back thinking how we process the information. Most of the time, we risk spending 80% of the time, managing and processing the data themselves, and only 20% of the time doing science. This is an example from conservation literature, and this is the number of publication growth in the years, and we have a decline of publications using field work and a very huge growth in publication using data analysis. And I think this is the reality we are moving into. We have a lot of time that we are actually playing with the data because we have to make them meaningful to us. At the same time, I am back to the question of, are the data we select meaningful, or are they still filtered by our ways of tackling the objective of our study? But in general, what we have to consider is that to actually make this data meaningful, we need to use models that are robust to outliers. And at the same time, we always have to remember that despite the fact that geomorphology is correlated and associated, this correlation and association, it's not the same at every level that we use to observe it, just as it's not the same at every scale that the process is happening to. And this was another example from bed load transport data, where they use different techniques to bind the information to get meaningful, to infer meaningful science from the sample bed load transport data. One thing to always keep in mind is that despite the large amount of information we are getting daily, there are some variables that are meaningful for us that will always be undersampled, and we might not even have ground truth to validate the sample data. And one example is subsurface flow of water. We will always have plenty of point information, but we will not have the complete pictures. Most of the data are non-standardized and non-labeled. And when they do have labels, they are subjective and meaningful depending on the science or the phenomena we are observing. And I think what is important is that we as scientists are the one filtering the information, giving them a context to make meaningful science. So I think I might be too quick, but we are at the point where big data is not really a problem, meaning that we will always have more and more. And I thought this publication was interesting, speaking about the definition of big data, because most of the scientists did not know how to define big data. Big data were defined with the V's that I've showed you at the beginning: volume, velocity, variety. Some didn't argue on how many V's. It's big data. But at the same time, nobody of the interviewed people were able to give a clear definition of what big data was for their research. Mostly, they were describing how they use data. But all in all, big data was highlighted to be a shift, an evolution of the science. Even in my mind, we are at the point where big data, it's not really a physical thing. It's mostly how we are working with reality. And we can get good information out of it, but we need to process them correctly. And to do so, we always have to keep in mind that the science we're doing, it's peculiar. Each process has its meaning, its way of working, and its evolution. So from the very large volume of data that we can get today, we have to get a digestible knowledge. We do need velocity of information so that we can, at least at some point, capture what we want to look into. And real time is critical for many informations, but it's not always critical to actually capture what the process we are looking into. We have thousands of data sources. We have to consider how plausible the response of the data is and how we can get knowledge from it. And this requires us to have an interdisciplinary and multidisciplinary background. And if not, to network as much as we can with people that might not have our background, but might complete our skills. And to do this, we need open ways of communicating and probably sometimes better ways of communicating. We always have to consider the uncertainty of the data, and we have to find a way to characterize it. Otherwise, other people cannot repeat what we have done. And understanding the uncertainty of the data gives us robustness of what we are doing. But at the same time, if we can get meaningful pattern and knowledge, we can give the data back for others to be used. So we can produce benchmark data set that others could be used. And I don't know if this is, a critical view that I have. Sometimes for these benchmarks, we don't need new data. We just need to polish what we already have so that others can use them. It's not necessarily adding in terms of amount of information. It's adding in terms of the quality of the information that it's already there, but we cannot tackle. Thank you.
Thanks very much, Giulia. That was absolutely fascinating. So you've kept perfectly to time. So we have about 5 or 10 minutes for some Q&A. So I'd encourage people in the audience, if you'd like to ask Giulia a question, you can post it in the Q&A tab at the bottom of your Zoom window. And to start things off, we have a question asking, do you think we need to focus on less covered areas of the world for information that hasn't received much attention, rather than assuming the drinking from a fire hose situation applies everywhere?
That's a very good question, and actually something that I thought as well. I think drinking from a fire hose happens in areas that are continuously flooded, and there might be people which still have no access to water in reality. Um, there is a very big digital divide in every different levels of life in terms of data access, technology, accessibility, tools to access the data. And this divide, it's a social thing, it's a political thing, it's also a funding scheme to where maybe if you're lucky and you end up in a university that sees the value of investing in something, you have more access to it just because there's more funds for it. So yes, definitely, it would be great to invest to increase the coverage and the accessibility and the way people can access information almost everywhere.
Brilliant. And we've got a couple of things from Martin Dawson here, pointing out that many organizations have now moved beyond concerns of sharing in defined formats and are more concerned with transformation and processing. And also recognizing that there are challenges posed in this presentation that are identical to those experienced in other fields, so that perhaps we can learn by example. So I don't know, Giulia, do you have any experience of speaking with researchers in other disciplines who are facing similar challenges to us as geomorphologists?
Uh, yes, actually. For something completely unrelated, yesterday I was talking to a friend. He's a pure data scientist. He works for industry and big data in industry. And I don't know anything about what he's actually doing, but the end of the conversation, the question he was asking me was, do we really know what these big data are? Like he was hired as a big data scientist to handle large databases of industry information in terms of market, in terms of productions. And at the same time, I don't work really with big data. I feel like we all say we have now access to big data, but we still do field scale science, which is actually important. But it is very hard to make um, global, meaningful science because that wouldn't make sense actually in my mind. We still have to start from small and then enlarge the picture. And then the other question was about transforming and processing. I guess, yes, that's the case. I don't have direct experience with transforming and processing the data. I'm back in Italy, for example, now, and in terms of data sharing, so I worked in Connecticut for many years and I'm still work with Connecticut. I know where to get all the informations. If I want weather data, if I want rain data, if I want climatic models, if I want public authority information on weather and hazard. And when I look into Italy, for example, and I want to get the same information, I get very specific researchers sharing very specific data. And then we have, so for weather, local realities, sharing local weather, which is not in the same standards if it's done by one region or the next one nearby. So definitely, I think data sharing is needed and it's always have to be there, but we should put more care into how we share this information. I feel like there was a boost on let's share whatever we can because we have to, and it's better to have it shared, and less care into let's share so that others can actually use it. And I'm also, even from my experience myself. I lack on that, meaning that I create codes that I need to make run for myself, and then I can share them, sure, but they're not ready to be used by others because they're not built for others to read. They were built for me so that I could get it done. And as of
Excellent.
learning by example, I think we always have to learn by other experiences. Doesn't matter the field we're working in. Most of the things I showed in the presentation, I did find them by even searching big data in science. There were many, many works on the issues or the challenges and the advantage of big data. And I think they are all consistent. It doesn't matter if you're a morphologist or hydrologist or an environmental scientist, they're all consistent all over. So maybe we should open more communication lines in terms of standards and methods that go beyond the discipline.
Excellent. And we've got 3 more questions come in, which is excellent. So the first of these is asking about the use of machine learning models for computing susceptibility or making predictions for things like landslides or flooding. Do you think these are meaningful methods, and are the results useful?
That touches me personally. I'm trying to use machine learning for geomorphology, and I received very tough reviews on this exact point. Are they, can we do machine learning to predict things that sometimes are outliers, they're not really predictable? Or are you overtraining because you're sampling and using to train, landslide, which is already the phenomenon itself, things like that. So yes, they are useful in my mind, in my opinion. We can go there. We have to at some point. We cannot always use linear models or non-linear models because the complexity of reality goes beyond a one-to-one relationship. I feel like we always need to highlight the limits. Let's say I'm training my model to predict changes from gauge data, changes in river flow from gauge data. Even by using the gauge data, I am biased because gauge data are distributed not homogeneously everywhere. So my machine learning model can work perfectly in the training side and in the validation, predicting based on the data it's fed onto. So the fact that gauge data are limited is a limit of the model, but it is a limit on any other type of science that you can do from those gauge data. You just add a bit more uncertainty because the model learns from whatever you feed into it.
Okay, excellent. So we're coming to time, Giulia, so we'll let you off the hook soon from all the questions. So we have 2 really good questions that have come in the Q&A. One asking about whether the next focus of our community should be on setting standards for benchmark data sets, and another asking a similar question about where we should focus our efforts in terms of developing skills and technological advances. What I'm going to suggest is that those are really great topics for people to discuss in the breakout sessions. So we won't put you on the spot directly, Giulia.
Okay, I'll put a note on this though because I like this question.
And then the last question we have, just one that's coming in the chat, is whether you have any views about accessing old kind of pre-digital data and kind of making that kind of data available, particularly when it's not available in English.
Yes, I have to work myself with old scanned copies of maps. We did a very big effort of making them semi-digital by scanning, but that knowledge might get lost at some point. So there should be, but I understand it might be a very big effort that's not many people would see worth in terms of volume of work, but there should be some effort to make even old information available that doesn't make it, you know, not meaningful information just because it's old and it's spread digital. It actually might be more meaningful than the digital one for some locations where we do not have physical access anymore or landscape changed since that first field survey that was done. And yeah, I'm not talking just about English works, of course. I think many US and European country are moving towards that way, but I feel like the world is much, much bigger than that. I mean, not just I feel, the reality is that much, much bigger.
Wonderful. Okay, so I think we'll leave things there